Good morning, everybody. Got halfway into the lab setup and discovered that the scales that we need to use for the lab half of them are broken. Apparently, either they got dropped or kicked or something in moving the stuff over from the old building to the new building. But that meant that we only had like 3 or 4 lab setups for 6 groups. So at 9:15, I discovered that I had to pivot. So we're pivoting to finishing chapter 29, and that sets us up for being able to start chapter 30 tomorrow in lab, which is a good thing because chapter 30 is a pretty healthy chunk of information. So what I thought I'd do is do the chapter 29, finish that up, and then I want to show you this. Ran and grabbed this setup so that we can see right-hand rule, how it affects charges, all that kind of stuff in a real experiment. And then we will have the rest of the time if you want to work on homework, that sort of thing. So that's kind of how it's going to go today. I expect this lecture portion to be maybe 40 minutes-ish. And then we will have time after that. Yeah?
Oh, okay. So we'll be able to complete the homework after this.
Yeah, I think we'll have a good couple hours if you want to use it to finish the chapter 29, because I'm sure that you guys have questions. I'm not sure I've lectured in this room yet, so it's going to be an adventure. See what works and see what doesn't. All right. So going back to the beginning just a little bit. Does anybody choose to remember this? Gauss's law, right? Chapter 20, was that 3? Okay. Where we had sort of a slick way to figure out what electric fields were, right? This is the integral that you see that you don't do. And sometimes you have to integrate to get the charge. And then briefly sort of talked about it, okay? But the version of Gauss's law, the strict version of Gauss's law for magnetic fields, though important, doesn't give us any kind of problem-solving ability. So the very first integral up there says a lot. Among the many things it says, it's that electric fields begin and end on charges. Now, I know it kind of doesn't look like that when you look at the integral. You're thinking Gaussian surfaces, you're thinking all that stuff, right? But it really does say that electric fields, the flux through any closed surface, can have a source, that source being a piece of charge. However, if we try to write down the magnetic flux for any magnetic field, what's like the chief distinction between a magnetic field and an electric field? What do magnetic fields do? They loop, don't they? They're closed loops, right? A magnetic field, it doesn't start on a north pole. It doesn't end on a south pole. It's one continuous round. They come out of north poles, they go into south poles, but there's no source. There's no magnetic charge that exists. And so Gauss's law for magnetic fields is important as a statement about the distinct physics that separates a magnetic field from an electric field. But as far as using it, usually when something equals 0, it's not typically useful for problem solving. There'd be no way for us to ever figure out what a magnetic field is, right? From that statement. Instead, what we have is the Biot-Savart law, that horrible cross-product-y thing inside of an inner, right? And that big mess. So Ampere's law is an attempt at doing what Gauss's law does for electric fields, but for magnetic fields. What I mean by that is it's not going to use flux. We're going to use something else. But it allows us to do a very quick and short version for finding a magnetic field. And again, we are not going to do the integral that we see. Sometimes we may have to integrate to find the current enclosed, but we're really not going to do the line integral that you see on the left-hand side. So what does Ampere's law state? Well, again, a little bit like Gauss's law. Instead of a Gaussian surface, we're going to have an Amperian loop. This is a mathematical construct that we get to pick. We get to make the shape of the loop no matter what. And if we pick it kind of cleverly, and I think you know what that means by now, right? Like, we know that magnetic fields go around in circles. So what shape do you think we might want to pick for a loop that's totally under our control so it matches up the best? We pick circles, right? If we've got straight line magnetic fields, then we pick squares, right? And that's really kind of the limit of it right there. But functionally, conceptually, Ampere's law allows us to do the same thing that we can do with Gauss's law, but do it for magnetic fields. For those of you just coming in and wondering just what the heck's going on and why lab didn't happen, lab isn't happening because the equipment's broken. So I'm pivoting to lecture, and we're going to, the slide you can't see, again, just as I didn't point it out at the beginning, we are going to do lab whatever it is. I can't remember the number, but we're going to do Faraday's Law lab next week. I'm going to start talking about Faraday's Law tomorrow and Thursday. That'll make us ready for Faraday's Law. We'll get that all done before spring break, and then we should be ready to go, right? So we might skip force on a wire altogether because the equipment's broken. We have to make up the circuits lab though. So anyway, I'll sort it all out, right? But we're going to go to Faraday's Law lab next week. So we've got this week, we've got next week, and then it's spring break, right? And then you come back from spring break and we have our exam, which is kind of really nasty, but it is the way it is. So I want to make sure that the Monday we come back from spring break, we don't have a lab to do. Like, we can come back, review for the exam, get our brains back on physics track, right? And then we've got Tuesday to review, and then we take the exam on Thursday. Does that make a little bit of sense? That's what I'm attempting to do. So we're gonna do Faraday's Law next week. All right. So back to Ampere's Law. Just how the heck, right, do we do this? I do have a video for this one. Let's see if the audio works in here. Wouldn't that be a shocker? Let's get this down. Play that. Let's see what happens.
The current in a straight wire creates a constant magnetic field. And since the field is constant on each circle, the line integral on each one is easily calculated. It's equal to a constant times the current in the wire.
I gotta get me one of these. Or is this called AI?
The result is the same for any circle around the wire, and for that matter, for any path around the wire. The line integral of the magnetic field around any closed path is always equal to mu naught times the total current that threads through the path. This is called Ampere's law, and it's one of the fundamental equations of magnetism.
Ampere's law. Depending on which side of the Atlantic you're on, it's either Ampere's law or Ampere's law. Got to get our vowel signs right, correct? All right, so what I wanted you to see from there, right, is that picture of the magnetic field, those blue circles, right? And then we're going to draw this Amperian loop. They've got a yellow circle right there to try to match those circles. And we're going to use that, right, that sort of geometrical construct, just like we did with Gauss's law, in order to figure out what a magnetic field is. But what's really the only thing that matters? Just like in Gauss's law, there's only one thing that matters. What is it? The current enclosed, right? If the current is enclosed by our Amperian loop, then it's good, right? We use it. What if there's currents outside this loop? We can ignore them, which means we can now find magnetic fields inside wires. More on that in a bit. Okay. So let's do an example. One that we already know, right? We already know how to, we know the magnetic field of a wire. We found that before. We did the horrible Biot-Savart thing and found the magnetic field of an infinite wire. We're going to do the same thing, only we're going to do it, come on iPad, we're going to do it using Ampere's law. So let's see here. Ampere's law starts with this integral on the left-hand side that we're never going to do, right? And so let's see here. I'm going to draw, so here's a wire, okay? And it's got a current I in it. I don't know. I'm just going to say it's the current is flowing into the screen, okay? Which means that I know that there's going to be magnetic field lines sort of around it, right? Let's see, which way would those magnetic field lines be pointed? Ampere's law can't give us any direction, so what do we need to find the direction of a magnetic field? Yeah, we need a right-hand rule, don't we? Okay, and we're finding a field direction, so it's going to be a hitchhiker type right-hand rule. So what does my thumb mean if I have a straight wire going into the screen? Is my thumb the current or is my thumb the field? It's the current. If it's a straight wire, you have a straight thumb. So you put your thumb in the direction of the current and fingers wrap around, in this case, clockwise, don't they? Okay. So I know my magnetic field is going to go that direction, which is handy for the direction. But Ampere's law should be able to give us the magnitude of this magnetic field at whatever distance we want to go. So what we're going to do is we're going to draw an imaginary Amperian loop, and we'll give it like a radius r from the wire. And we're going to go to town, right? The line integral of the magnetic field dotted into the sort of path integral as we go around this circle. Well, we know, like if we make ds go around like this, well, that's the same direction as the magnetic field. The angle between those magnetic field vectors and the path vectors are going to be 0. Cosine of 0 is 1. So this literally turns into b times the integral of dl. But then if you break up a circle into a bunch of tiny chunks and you add up all the tiny chunks, what are you going to get? The circumference of a circle, right? So b times 2 pi r, right? Make sure it's a circumference, not an area. It's kind of an easy mistake to make because it feels so much like Gauss's law, right? But it's not. We're doing magnetic field times a length, right? A path. Vectors go away. It's a dot product. And dot products make vectors go away, right? Very handy that way. Okay, so what we need on this side is a constant, and then we need the current enclosed. Well, in this case, that's just whatever current is flowing in my wire, isn't it? There's nothing else. If I had 2 wires, I'd put in both of those currents. What if those wires were going opposite directions? What if we had a case where we had, say, current flowing in and current flowing out, and both of them had identical currents, but they just had opposite directions? What would the current enclosed be? It would be 0. Now let's think about this a different way. What direction is the magnetic field from the black wire with the current going into the screen? It's around, but which way around is it? It's going around clockwise, isn't it? So the black wire is doing something like this, right? But what direction is the blue wire's magnetic field going? Counterclockwise, right? If we take our thumb pointed out of the screen, it wraps around counterclockwise. So that means we have an identical field, but this one is going counterclockwise. What's the net field going to be from these two wires? It's going to be 0, which means that the current enclosed has to be 0. So if you have currents going in or out, right, you got to kind of pick a direction that you want to call positive. But if you've got 3 going in and 2 going out, your current enclosed is 1 going in, right? No, as long as it's enclosed by your Amperian loop. That's all you got. That's all you got to know.
How do you know which ones cancel the 3 and which ones don't?
Well, you decide. You call into the screen positive or out of the screen positive. It doesn't matter. You just get a minus sign. All right. So my current enclosed is just I. And then my magnetic field is going to be mu naught I over 2 pi r. Now, if I go back, if I can find it in my notes, the magnetic field of an infinitely long current carrying wire is right there. What do we get? It's the same thing, isn't it? Okay, which again, hopefully comes as very little surprise. I mean, we're doing the same physics. It's just one way we brute forced it with the Biot-Savart law, defining this little tiny piece of current and then adding all that up. But here we are able to do sort of an end run around the complicated mathematics by having more conceptual load. But I'm hoping this time the conceptual load is just a little bit easier because we've done Gauss's law before, right? And we don't have all the complexity of like flux to worry about, right? Electric field passing through an area. All we're really doing is matching up circles, right? So, excuse me. So what is your left-hand side almost always going to turn into? B times circumference of your path, right? And most of your paths are going to be, I'm going to do an example here where it's a square path, right? But we just do magnetic field, right? It's all circles. And so it's always going to be that. And then on the other side, however many currents you have, right? Before, if we didn't have Ampere's law, we'd have to find the field from every current, right? And I did an example of that, right? Where we had different wires and I had to find the fields at different places and add them all together. Well, this way we just do current enclosed and we've got our magnetic field. Okay, what's that?
What about like spheres?
Spherical wires. It's got to be a current, right? And currents typically flow down cylindrical wires. Spherical wires don't work so well, seeing that they don't have ends, right? So, okay, so what do we do if, say, instead, this is our wire, right? And we want to find the magnetic field inside of our wire. Why would we want to know the magnetic field inside of a wire? What possible use could knowing the magnetic field inside a wire be? Do any of you have internet at your house? Probably, right? And I'm going to guess that most of you are getting that internet from Comcast, Xfinity, maybe AT&T, which is slightly different, but the majority of carrier, the carrier we have in Fresno, the monopoly, because of course free markets exist here in Fresno, is that we have Comcast. So Comcast is cable internet. The cable that runs into your house is called a coaxial cable. And what that means is it's got a conductor down the center, and then it's got like a plasticky nylon structure. And then around that plastic nylon, there's another metal sheath. So the two conductors are a conductor down the middle and then a return conductor that wraps around the outside. It's called a coaxial cable. And it's really good in high bandwidth situations. High bandwidth meaning you can carry a lot of information on the carrier signal that goes down the cable. knowing the magnetic field inside of this structure is very important because magnetic fields can affect the flow of charge. And if charge is being affected in your current carrying wires, it's more difficult for signal to propagate down the wire. So having the ability to predict what's going on inside of these structures is really important. So that's a direct application of what's going on here. So if we have a current, right, and we are going like we're inside of this current carrying wire. We want to know the magnetic field inside of this current carrying wire. Well, I still use Ampere's law, right? The challenging part is finding what the current enclosed is. My left-hand side is just B times 2 pi R inside, right? But the current enclosed here, we have current I throughout the entire wire itself. But I need to find the fraction of current that's actually contained inside of my Amperian loop. And so I've got to get a little bit clever about that. Current, by definition, is the amount of charge, right, per area in a conductor, right? We're counting the amount of charge that goes by. It's charge per time, right? We're keeping track of the number that flow through per second. But it's through the cross-sectional area of the wire. If I get a bigger wire, I get a bigger cross-sectional area, I can carry more of that charge through it. So you can set up a ratio I enclosed divided by the total current, I'll call it I naught, that's going through the wire. That is going to be equal to the ratio of the cross-sectional areas. So the R enclosed has a radius R inside, so the cross-sectional area of the wire. And then the whole wire is pi, we'll call that big R, the actual radius of the wire. We'll call that big R. So this comes from the definition of current density, where we have current flowing through a cross-sectional area, and the current density has to be uniform if it's the same current throughout. So we can get to this. You don't need to really kind of understand the stepping stones there, but it is nice to know that if your current is uniform, if there's no doesn't change as R squared or anything like that, your current enclosed is just going to be equal to the original current times R inside squared over the total R squared. The pi's cancel out, all that kind of stuff. So for uniform currents, you can just set up that simple ratio. If your current isn't uniform, if it changes as a function of the radius of the wire, like say there's no current in the middle, and then the current gets bigger and bigger as you go outside the wire, what do you get to do? Infinitely many. You get to integrate. And you've integrated over a cylinder before. So anyway, that's our I enclosed now, which means that B times 2 pi R inside is equal to mu naught times my original current times R inside squared all over R squared. So one of these R insides is going to cancel. My 2 pi is going to come down below. And I'm left with the magnetic field inside is equal to mu naught current in the wire R inside all over 2 pi big R squared. So that equation there in the box gives me, for a uniform current density, gives me the magnetic field. Let's check some things first. What happens if we go to 0? If we get to the center of the wire? Then there's no magnetic field there, right? But that makes sense because there's no current enclosed if we have If we're right at the center, then the radius of our Amperian loop is 0. There should be no magnetic field there. So I like that. And then as we come out, and if we if we set sort of inside and outside equal to each other, then we'll get, where the radius is big R, we will get the same answer. So they're consistent across all regimes, which is always a good feature to have in physics. So that's kind of an overview of Ampere's law. The good news for you is I've kind of done almost all of them now. The geometry is like, Lewis asked, are we going to do a spherical one? Well, no, because there are no spherical wires, right? Most of the time we don't make our wires out of like a square cross section, right? They're all cylinders. So we're limited in the geometries that we can solve, so we might as well solve them all. So I want to do the other geometries that are out there so that we can sort of complete all of our shapes for magnetic fields. So this right here is a solenoid. It's a very big one. It's many turns of wire that is generating a magnetic field. I'll show you how this device works later. Do I have any solenoids close by? No, you guys saw some solenoids in your magnetic field experiment. So I know you've seen them before. But basically take some wire, wrap it around a cylinder, right? And you get something that makes a magnetic field that looks an awful lot like a bar magnet. So what we want to try to do is explain how that happens. We want to find the magnetic field of a coil, and then a solenoid is just a bunch of coils, right, that are stacked up. So what I kind of have to do here, which is a little bit hard for me to draw, right? A solenoid will be all these loops of wire, okay, coming together. I need to be able to draw that sort of in cross section. I need to be able to cut the solenoid along its length and draw what's going on there. So I will attempt to do that now. You know what? I better make those bigger. So if I cut the solenoid in half, kind of like I'm taking a big piece of French bread, and instead of cutting it up into little pieces, I do that one big slice through the middle that gives me two very long pieces of bread that I can make a big sandwich in or something like that. I've kind of cut my solenoid like that. I've just sliced through it the long way. And that means that if I've got current that's flowing around these coils of wire, the current coming out of the top half and the bottom half has to be opposite in direction. So I've got this circular flow of current. The current's coming out at the top, goes in at the bottom, comes out at the top, in at the bottom, out at the top, in at the bottom, spiraling all the way along. It's one single piece of wire that gets coiled up into this solenoid type structure. The magnetic field, as you measured it, let's make sure I get this right, yep. The magnetic field that you detected in that Discovering Magnetic Field laboratory had a very straight magnetic field inside the solenoid, and then around the outside edges, it started doing, wrapping around and doing the north-south pole out kind of stuff. What we're going to do is we are going to concentrate on inside the solenoid, and we're going to just think about an effectively infinitely long solenoid. We try not to do edge effects in Physics 4B because they get pretty complicated. So we want to find the magnetic field inside of a solenoid. That's our goal. And we're going to use Ampere's law excuse me, to do it. Okay, again, the challenge isn't the left-hand side. Left-hand side, what are we going to do for the left-hand side? Oh, yeah, we can pull out the B, but what are we going to do for the DL? Well, we can't do anything until we get our shape down, right? Our Amperian loop shape. But do you see how that magnetic field is straight inside of that solenoid? We don't want to use a circle now. We want to use a square. So we're going to make an Amperian loop that only encloses one side of my solenoid. Why don't I want both sides? They'll cancel each other out and I'm not getting anywhere, right? So I'm going to just look along one side. What can you tell me about B dot dl on both of these sides? Remember, there's a dot product in there. Well, not only are they not vectors, they're a very specific number. It's 0. Why are they 0? Right? Like if we're going around our loop this direction, right? Both sides, the directions are up or down, but what direction is the magnetic field? To the right or left? It's horizontal, isn't it? What happens if you try to take a dot product between two perpendicular vectors? They zero themselves out. So the integral of B dot dl is going to be equal to 0 on that side, this side, and the bottom side. Why is it going to be 0 on the bottom side? There's no magnetic field there, right? The magnetic field's inside the solenoid, not outside the solenoid. And so I've just handled 3 of the sides, and the remaining side, the side that's up here, that's pointed in the same direction as the magnetic field, well, that just turns into B times L, the length of one side of my box, right? All right. So now I've got that side figured out. That wasn't too bad. Oh dear. How are we going to handle I enclosed? How many do I have enclosed there? Looks like 5, doesn't it? Okay. But that's okay. That's all fine and good for this solenoid. But what if I had another solenoid that had like smaller wires or bigger wires? Yeah, there'd be different kind, right? I want to try to write this down. I don't want to solve it for just this one solenoid. I want to be able to write it down for all solenoids, right? So the current in these wires is I, isn't it? Each one of these has an I in it. And as I pictured it here, I have basically 5 times I, right? 5 currents inside of my box. But if I had drawn my box bigger, it could have been 10. If I drawn my box smaller, it could have been 2, right? Or a half or something, like it could be anything, right? So how do we capture every situation that we possibly can? It's well, let's not integrate if we can help it. This is 5 times the current. If I drew my box smaller, it could have been 2 times the current. If I drew my box bigger, it could have been 10 times the current. What's the pattern? Like X is like just some integer number, right? Times the amount of current I've got flowing in the solenoid. So instead of X, physicists don't like using X for these kinds of variables. It's like a variable that's not really a variable. It's not like X that gets usually integrated against or is like an infinite number of places in space. This is more of a counting number times the current. So we tend to use capital N as a generic counting number. N, or as you'll see in Physics 4C, M, the letter M as in mom. Both M and N can be used as generic counting numbers. Okay, so I've got my current enclosed, right? It's going to be however big my Amperian loop has been, right? However many that encloses. And now we've got a little bit of an issue, slight issue. You'll notice that our dimension for our Amperian loop, this L, this Amperian loop, which is supposed to be just this mathematical construct that we really don't want to have any lingering part of that mathematical construct left behind, because again, it's something we made up. It's just a conceptual framework for us to try and get solutions to real things in real space. Well, now it's included in our equation, which is slightly disturbing. I won't go into why, but in physics, we don't like this sort of thing. So what we do is we write it like this. What did I do? I just changed symbols. Gets rid of the problem. Well, sort of, okay? Curly little script N there. The number of turns per unit length. That is a ratio that is very real for a solenoid. So if I come over here to these solenoids, big, huge solenoids here, okay? This thing is about 1 centimeter wide, okay? And if I count the number of wires, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 wires, 11 turns, okay, individual wires that I counted, in 1 centimeter. So my number of turns per unit length was 11 turns per centimeter, right? And then, of course, I'd want to convert that to what to do all my math? You want to get the centimeters into meters, right? So it's not the fact that this actual solenoid is a meter long. That doesn't matter, okay? What matters, right, is the number of wires I have per dimension for my solenoid. If I got really, really fine wire, that number could run into the hundreds per centimeter, right? Or tens of thousands per meter. And then if I have really big, thick wires, right, that would be just very few per length. So that captures whatever number of solenoids and size of wire I might have. It's all captured in this idea of the number of turns per unit length. And then I can just find the magnetic field at the center of my solenoid. If I know the current in my solenoid, I know the number of turns per unit length, and I know what universe I'm in, mu naught, 4 pi times 10 to the minus 7, boom, I'm done. I've got the magnetic field of a solenoid. And this way of doing it, this way of going at it from the point of view of Ampere's law, saves us all of that Biot-Savart horrible integration stuff, right? Where we'd have to break this whole thing up and find cross products and all that sort of stuff. Okay, so how did I know the magnetic field was going to the right? Did anybody catch what I did as I was drawing my picture? No, you didn't see it? I did it. Yeah, I did a right-hand rule right as I was drawing my picture, okay? The way that you find the direction for a magnetic field in a solenoid is the same way that you would find the direction of a magnetic field of a coil of wire. So again, we are talking about fields. So that means we are doing hitchhikers. There's no forces here, right? We just want to know the direction of the field. So it's going to be a hitchhiker. But what's the shape of your wire this time? It's coils, isn't it? So what does your thumb mean? It's not the current. It's going to be the magnetic field. Your fingers curled around are going to be the direction the current is flowing, because the current's going around in circles. So the current comes out of the top of the screen. My fingers come out of the top of the screen. My fingers coil around and go back inwards at the bottom. Which way is my thumb pointing? To the right. So you find the direction of a solenoid. So like if I knew, say, that the current in this coil is flowing around this way, right? I've got these big circles here. I would wrap my fingers around the direction the current is flowing, and I know that the magnetic field would be along this axis down here at the center of my solenoid. So directions by right-hand rules, and magnitude of magnetic field in a solenoid found by what it turns out to be a pretty simple arrangement, 3 things, 2 of which are constants. All right, let me cue up, because we're going to take these solenoids and we're going to turn them into other things.
The net result is a field that goes in circles. The lines of force are circles Concentric with the
Oh,
wire,
it's breaking
and the
up here,
field is
too.
the same all the way around each circle. On the other hand, if the wire is bent around into a loop, the current flowing through it produces what is known as a dipole field.
Right, current was going that way. Field goes that way. All right, so there's your loop. So they showed us a wire, which had those circles going around it. If we take that straight wire, we bend it around into a circle, we get a magnetic field pointing up in the center. Of course, they form circles, so they go around, but it points up in the center. Now they're going to take that loop and they're going to extend it into a solenoid.
A helical winding, or solenoid, is like a stack of current loops. It creates a field much like that of a bar magnet.
Right? So do you see those straight lines inside? That's what we just solved for, right? And again, we find the direction. It was flowing around this way. So I wrap my fingers around the direction of current flow. My thumb points up, which is why they've got an arrow up there, which indicates the top side of that solenoid is the North Pole. All right, so now that we've got our helical winding, what happens if you bend that around into a circle?
If the solenoid is bent around into a circle, the donut it forms is called a toroid. The magnetic field of a toroid is contained completely inside the windings. There are no field lines outside at all.
So if you don't want any magnetic field to get out, what do you make? You make a solenoid that's bent on itself, right? Otherwise known as a toroid or a torus, a donut. I like calling them donuts, even though I don't like donuts. Okay. So the place you're going to find these most often are inside power supplies and computer motherboards. Your phone does not have a toroid in it because it uses a different kind of power supply. It uses a battery. But if you've plugged into like AC power and you have a computer that runs off the wall, then somewhere in there, there is going to be not one, but several of these. Because you need solenoids in order to clean up electrical power signals. The power signals that come from PG&E are kind of dirty in the sense that they fluctuate in their voltage, and sometimes they don't push enough electrical energy and sometimes too much, and there's this variation. It's a natural part of how, just pushing stuff down wires. There's always going to be this noise. What the computer's power supply does is it cleans up that noise, because the CPU, the graphic card, the memory, they all need very consistent amounts of electricity. You get too much electricity when you're going to read and write into a memory module, you could end up having, Tolstoy for your essay instead of your own words, and then your teacher's going to, no, well, it's not that big a deal. But you get bit flips and all kinds of stuff, and it can all go wrong. So you want these nice, steady currents flowing in those chips. One way that you can stabilize voltages and currents, as we're going to find out next unit, is that we use solenoids to do that. Problem is a solenoid is going to make magnetic field. And until recently, you didn't want magnetic fields anywhere near your computing devices. Because how do hard drives store information? Magnetically. Okay, the 0 and 1s are represented by magnetized portions on the surface of the disk. And so if you had solenoids that were cleaning up your electricity, they could theoretically rewrite your hard drive's information in a way that you didn't want. So to get around that, you take those solenoids, you turn them into toroids, and that keeps the magnetic field from leaking out into places that you don't want it to be. Flip side of this is that's the shape you need in order for fusion to work. In order for fusion to happen, we need to put the sun in a bottle. Actually, we need to put, here on Earth, we need to put roughly 30 times the temperature of the sun in a bottle. Okay, sun's inner core temperature is like, I can't remember what it was, like 30 million Kelvin or something like that. and we need to do something like 150 million Kelvin or something in our reactors to get the sun has a lot more pressure density. We just can't make that kind of pressure here. So how do you take something that's hundreds of millions of degrees and put it in a bottle when tungsten is the thing that's got the highest melting point at around 4,000 Celsius? Well, the answer is you don't put it in anything material. You put it in a magnetic bottle. This is a magnetic bottle. So you make a tora, you make a big solenoid, okay? And you can take those magnetic fields. And why would the plasma that we're heating up to really high things, it's all full of charged particles. Why would charged particles stay inside of a magnetic bottle? They experience forces from magnetic fields, don't they? So that's what I want to show you now. I want to show you this demonstration since we're here together in lab. To do that, I do need to turn the lights off. I need to kind of get it dark in here. And I need you to come up in little groups, maybe just what we need to do is we need to surround this cart so that you can see this glass globe. So I'm going to kind of cut the room in half here. So this along this line, this half of the room, let's all get up and gather around this. I'll do this twice, right? So don't worry, don't worry. Yeah, if these guys die, class is dismissed. I'm going to turn off the recording. We don't need the recording right now. And the second half of the room is going to benefit because